Good morning, everybody, and welcome to the online CEIA maths tutorials again this week. This week we've got two sessions, one in the morning and one in the afternoon, covering the exam papers, paper 1 in the morning and paper 2 in the afternoon. For the morning session, we've got Suzanne O'Callaghan, who we've met before. She's a researcher in Tyndall, and she's going to take paper 1.
Good morning, everyone. I've met you previously with geometric or sequences and series, so I hope you enjoyed that topic. So today what we're going to do is work through a sample exam paper. It's a previous mock paper, so the questions are probably a little bit more challenging, but they will definitely help you to get a better understanding of a particular topic. So we'll work our way through them, and I'll take questions as well. So typically for paper 1, these are the kind of topics that you expect to see. You've got complex numbers, algebra, functions, induction, logs, sequence and series, differentiation, integration, trapezoidal rule, financial maths, and rates of change and average values. Now, the one thing to note is that these are guidelines. In the past, you could depend that only those topics would show up in paper 1. But what's happened in recent years, you've probably seen whereby sometimes a topic that you would expect to see in paper 1 shows up in paper 2 and vice versa. So you really have to be prepared going into both exams that you have both all of your topics covered, really, because the element of surprise is cropping up a lot more, I noticed, in the last few years. So this is an outline of the questions that we're going to do today from the paper that I have. And you can see question 1 is algebra, logs, induction. It's a nice question. It eases you into the paper nicely, particularly during an exam. You've simultaneous equations and functions. Again, not very challenging and a nice way to gear up in a paper. Then you come to roots of equations. Question 4 is on complex numbers, polar form, and De Moivre's theorem. This is a really good question because it does cover, if you can do this question, you're going to be, you're fairly strong on complex numbers. Functions and differentiation, integration in the area under the curve. I've noticed that integration is taking much more of a hold in papers in the last 2, maybe 3 years, whereas in the past it was just a small 1 or 2 integrates. Now they're actually looking for more difficult questions like getting the area under the curve. Then in section B, you have log and exponential functions. Question 8 is financial maths, and question 9 is acceleration and rates of change, which would come from your differentiation. Right, so I will work systematically through from question 1 to question 4, and after that I'll jump down to question 9, which will be acceleration and rates of change. And then question 5, 6, and 7, we'll see if we have time to get to them. Right, so we'll move on. So question 1, we have solve 2x squared minus 11x plus 15. So there are some parts of the questions that, look, I'm not going to spend a lot of time on because I know you know how to solve them. They're just they're basic maths. So I'm just going to put up the answers here. Okay, here we go. So we have 2x squared minus 11x plus 15. So you'd go and solve that. I mean, you can get that by solving, and you'd have 2x in here, x in here. You'd have so our answer for it is x is equal to 3 and x is equal to 5 over 2. So that stuff I'm not going to spend time on, right? So the next part of that question is hence, and the important part there is hence or otherwise. Hence or otherwise solve 2 times 1 over t squared squared minus 11 times 1 over t squared plus 15 is equal to 0. So if you look over at the original one that you were given here, you'll see that the equation formats are actually the same. But this here looks like that's the equivalent of 2x squared. That's the equivalent of minus 11x. And there's your plus 15. But what's different about this equation is that in this equation, x is equal to 1 over t squared. So where you would have had x in the first equation, in this equation, you have 1 over t squared. So that means the solution to this equation is same as the solution to this equation, in that x is equal to 1 over t squared. And you have solved for x. You have got x is equal to 3, and you've got x is equal to 5 over 2. You've already solved them in the other part of the question. So now you can equate 3 is equal to 1 over t squared, and 5 over 2 is equal to 1 over t squared, and you solve. That's just simple algebra. And for that, you will get t is equal to 0.58, and t is equal to 0.63. So again, watch out for hence or otherwise. There must be some link between one question and the other. Now, show by induction that n into n plus 1 by 2n plus 1 is divisible by 6, for n is an element of natural numbers. So induction probably puts a lot of people off, but there are a lot there. It's one of the questions that's very easy to gain points by, because there are 3 steps that you must follow. If you even write out the steps, you've already achieved 3/4 of the points. So the first point that you always have to do is prove that it is true prove that it's true for n is equal to 1. Very simply, you put in 1 into 1 plus 1 times 2 times 1 plus 1. And that's equal to what? So it's 1 plus 1 is 2. 2 by 3 is 6. So the question is it divisible by 6? Yes, it is. So it is true for 1. Step 2, which is always the same, which is assume that it's true for n is equal to k. That's again very easy. You just slot in just by writing these steps: k plus 1 into 2k plus 1, and you're saying is divisible by 6, and you're saying it's true. You've assumed that it's true, which means that you can use this in the latter part of the proof to help you to prove that it's true for k plus 1. Okay, so there's nothing challenging in this except that you got to memorize the steps. You write down your step 1, you write down your step 2, and step 3 then is you have to prove it's true. But here's where the proof is: prove it's true for n is equal to k plus 1. Okay, so the first thing we do is input k plus 1. So we have k plus 1 into k plus 1 plus 1 into 2 times k plus 1 plus 1. And when we multiply all that out, we get 2k cubed plus 3k squared plus k plus 3 plus k plus k plus 6k squared plus 12k plus 6. Now, if you've noticed, I haven't added up all the k squareds yet. That's 3k squared. But if you look at this part here, there, it's 2k cubed plus 3k squared plus 6. Actually, sorry, my apologies, guys. I'll have to skip it instead. My assumption.
Suzanne,
Yeah.
sorry to interrupt you there. I've got a question from somebody in the audience asking,
Okay.
where does the K come from?
Okay.
Sorry about that.
No problem. Thank you for the question. So the K is just literally, it represents any number. So they're asking you to show by induction that n times n plus 1 into 2n plus 1 is divisible by 6. So the steps that are required is that you prove it's true for n is equal to 1, you give it a real number, and then you must prove it's true, you must assume that it's true for n is equal to k. So k just represents another variable that you have to prove it's true for any k. So in the steps that are required for induction, k is just introduced as the letter. It could be n is equal to y or x. So we're just picking that k as any variable. So we slot it in and we assume it's true for n is equal to k. And that's the formula that you have here, which is divisible by 6. So we multiply it out and we get 2k. We get 2k squared cubed. Plus 3k squared plus k. And because it's divisible by 6, we say it's equal to 6a. And now, for the person who asked about the question, who asked about k, now we're introducing another variable, which is a. It just represents that something, any other number that can be used. If it's multiplied by 6, well, then it means that it's divisible by 6. So 6a just represents another variable. So we're saying that we're assuming it's true for n is equal to k, which means that 2k cubed plus 3k squared plus k is equal to 6a. In other words, 6 times any number. It doesn't matter what number it is. But the fact that it's 6 times it means that it is divisible by 6. Step 3 is prove it's true for n is equal to k plus 1. That's going to be, like I said previously, k plus 1 into k plus 1 plus 1 times 2 times k plus 1 plus 1. And we have to prove that this is divisible by 6. So how do we do that? So first of all, we multiply it out and see what we get. And we get 2k cubed plus 3k squared plus k plus 6k squared plus 12k plus 6. So if we notice here in this part of it, the first part of it, 2k cubed plus 3k squared plus k is the exact same as this up here. See that there? And we have already assumed, because we've been allowed to assume that that is true. In other words, that 2k cubed plus 3k squared plus k is equal to 6a. So we know that it's divisible by 6 for that section. So we can replace this part here by 6a. So now we have 6a plus 6a squared plus 12a plus 6. Now this part here, we can take 6 out of it. And here we can take 6 out. So if we take 6 out of the whole lot, we have a plus a squared plus 12k plus 1. Is that divisible by 6? Yes, it is, because it's all multiplied by 6. So it is all divisible by 6, which is QED, which is what you write when you've proven something. Okay, so just to recap, these are the steps that you have to take. Learn them off. Step 1, prove it's true for n is equal to 1. Step 2, assume it's true for n is equal to k. And then the third step is prove it's true for n is equal to k plus 1. If you learn off each of those steps and then just follow by substituting in the values into the equation, when you get to the proof, remember, usually you can use what's been assumed to be true in step 2. That is always there to help you solve reach your proof at the end. So induction is very simple in one sense, in that even if you don't know how to prove it, and I would often have started induction questions not knowing how to prove it, even if you don't know how to prove it, you can still write down all the steps, you can input all your substitutions, and if you get stuck at the end in that you can't do your final proof, you've already provided 75% of the question, which means you get probably 75% of the marks. So please don't ignore induction. It's a case of learning off the steps and doing it. So if there's any questions, I'll go back over anything there. So we'll move on to question 2, which is simultaneous equations. Again, this is probably one of the simpler ones, so I'm not going to spend a lot of time on that, because triple solving simultaneous equations should be easy enough for you. I'll just show you the key point here in this question. So the problem here in this question is, for your simultaneous equation, they've given you one with fractions. So you're probably all used to dealing with 3 standard simultaneous equations. So the one that you have here has fractions in it. So that's okay, just bring it down and deal with it. So you've got 3x over 2 minus 5y over 3 plus 2z. 2z is equal to 2 over 3. So how do you tidy that up? Well, if you multiply across by 2, you get rid of the half here, but you're going to have a 3 here. So you multiply across by the lowest common denominator. So if you multiply across by 6, and remember, you have an equal sign here. So if you're going to multiply across one side, you multiply the other side by 6 as well. So that means you will get 6 by 3x over 2 minus 5y by 6 all over 3 plus 6 by 2z all over nothing is equal to 6 by 2/3. So what happens? So 2 divides in there 3 times, 3 divides in there twice. So you end up with 9x minus 10y plus 12z is equal to 4. So there you have an equation that you can work out simultaneously with the other 3. So just in case any of you, I'll just do a quick recap. What you do to solve these 3 simultaneous equations, you work out 2 together and you eliminate one variable. So you're left then with something in terms of x and y. So say you knock out the z by working on the two of them. Then you can work on these two here maybe and work out the z again, right? And then you'll be left with another x and y. And then you simultaneously solve between your two variable equations. You see, you have three variable equations. The three variables are x, y, and z. So what you need to do is knock out one variable first. So you get left with two sets of equations in two variables, and then you reduce it down to one variable and you solve. So move on to the next question. If anybody wants me to go back and do that in detail, I will. So the next question is, graph the functions f of x is equal to the modulus of x plus 3 and g of x is equal to 4. So you've got two equations here, two functions here that they want you to graph. The first one we focus on is the easiest one, which is g of x is equal to 4. So what's g of x equal to 4? Well, g of x is equal to 4 is the line that goes vertically down. Sorry now for not getting a straight line. That goes vertically down through x. Apologies. The other way around. G of x is equal to 4. That means anywhere that y is equal to 4. It's a straight line. So no matter what value x is, y is always equal to 4. That's your line, g of x is equal to 4. G of x is equal to 4. Right, now the next one that we have to draw is the f of x is equal to the modulus of x plus 3. So what does the modulus of x plus 3 mean? It means that any value we get inside that modulus bracket, if it's negative, it's made positive. So I'll give you an example. So let's start finding some values on that function. So always start, when x is equal to 0, what's f of x equal to? Well, it's going to be equal to 3. If x is equal to 1, f of x is going to be equal to 4. If x is equal to minus 1, f of x is equal to 2. If x is equal to minus 3, what's f of x equal to? I'm just going to demonstrate that one. It's the modulus of minus 3 plus 3, which is equal to 0. What happens when we have when x is equal to minus 4? Well, then f of x is equal to the modulus of minus 4 plus 3, and that's equal to the modulus of minus 1. But the modulus means that you only take the pure value, you don't take the sign. In other words, it just wants to know the actual size of the unit. So your answer to that is 1. So when x is equal to minus 4 here, we know that f of x is equal to 1. So it's up here. So we'll go back and plot the rest of them. So when x is equal to 0, f is equal to 3. Where it crosses the y-axis. When x is equal to 1, f is equal to 4. So when x is equal to 1, f is equal to 4. I'm working on PowerPoint annotation this morning, and I usually work on a whiteboard, but I thought it'd be easier to follow on PowerPoint. But the annotation tools have a lot to be desired. So what was I? X is equal to 1, f is equal to 3. X is equal to 1, x is 4 is there. X is equal to minus 1, f is equal to 2. X is equal to minus 3, f is equal to 0. F is equal to minus 4. So we had a positive there, x is equal to minus 4, f is equal to 1. I have to mark them with an X. For some reason, when I draw a dot, this other menu pops in. And let's see if we can get another one up there. When X is equal to, try this one, when X is equal to -8, what value do we get? F of X is equal to 5. So we have -8 here, and we'll go up, we'll take it to 5. Just 5. Now the next job is to try and draw the line. Right, apologies for being so wobbly. Okay, so that is the function f of x is equal to x plus 3. And do you see what's happening? Excuse me. Instead of the function continuing straight down in a straight line down here, this is all a negative area down here. Everything is minus. Y is negative, x is negative. So the modulus prevents it from going down through the x-axis. So by making everything positive, it kicks it back up again into the positive area, which is why you don't have a continuous function. You have what looks like this. Okay? So just to recap, because f of x equals the modulus of x plus 3, it makes every value in here positive. So when you're drawing the function, you see that it only exists in the positive quadrants, which is here. In these quadrants, x or y or both are positive. So that's why you get a shape that looks like that. So what's the question? Graph the function. So that's it. We've graphed that function. Now the next question on 2 is, using your graph, write down the solution set to the inequality f of x is less than or equal to g of x, where x is an element of real numbers. So what are they asking you there? They're actually asking you, where does it occur that the function f of x is less than or equal to g of x? Well, visually, it's very easy to see if I highlight it here for you. You can see here, down here, everywhere that the function f of x is under the line g of x, this is the area they're talking about. That's it. That's where f of x is less than or equal to g of x. If it were up here, it would be f of x is greater than g of x. Okay, so you can visually see it. But they want us to write down the solution set. So what's our solution set? Well, the way to find it out is if we knew what this point was, and we knew what this point was, because we know that it's everywhere from here down. It's within these 2 points, f of x is less than g of x. So that point, the point where g of x and f of x intersects is, that first point is 1, 4. The first point, 1, 1, 4. The point where they intersect here is actually -7, 4. So if you have drawn properly, like I don't, on your graph paper, you'll be able to read off those points. So what does that mean? So 7 is the x value and 1 is the x value. So the solution set, they're asking for the solution set with respect to x. In other words, what values of x, or between what values of x is f of x less than f of x, or less than g of x? Well, where that occurs is between -7 and 1. Put x in the middle. So where x is greater than -7, or equal to, because it is equal to as well. And where it's less than or equal to 1, that is your solution set. So I hope you all can see that. It's hard not to be able to get feedback from you, but the solution set for the question is that for all the values between -7 and 1, where x is equal to -7 up to 1, if between those values the f of x actually is less than g of x. Now, the next part of the question is they want us to verify it algebraically. Say, for instance, you didn't have a visual of the graph and you were just given the two functions and you needed to identify the solution set again. So this is our approach. Again, very simply. So they're asking you, f of x is less than or equal to g of x, and they want you to solve this. So we know f of x is the modulus of x plus 3. And so we still say it has to be less than or equal to. We know that g of x is equal to 4. So we've set up our equation. Now, how do we balance this equation? Well, because of the modulus, it becomes complicated. If we square both sides, it takes away the effect of the modulus. For instance, if we have a -3 by a -3, if they're multiplied together, we'll get +9. So anything squared will always go to a positive, which means that even if the modulus number was a -9 or a negative number, by squaring it, we're coming to a positive answer. So by squaring both sides of this equation, we're sure that we're not losing out on any values from the modulus. So if we square both sides, now be wary as well. The modulus is not like a square root, whereby if you square a square root, say if you have there, a lot of people get confused. If you square a square root, you're left with x, because the square cancels the square root. The modulus isn't like that at all. The modulus ends up being you have to have x plus 3 by x plus 3 is less than or equal to 16. So by squaring them, squaring x plus 3, you're able to remove the modulus, because we know that anything squared is always going to be positive, which means we don't need the modulus sign now. Okay, so when we square that, we get x squared plus 6x plus 9 is less than or equal to 16. And we bring our 16 across and we get x squared plus 6x minus 7 is less than or equal to 0. So we solve this, you get your factors, and you get x plus 7 and x minus 1 are less than or equal to 0, which means that x is equal to -7 and x is equal to 1, exactly as we found up here. Okay, so that's how to find your solution set algebraically. You just substitute in the actual equation for the f of x and the g of x and work down your inequality. Okay, so I'm going to move on from that to question 3.
Sorry to interrupt you there, Suzanne. I've got a question in from a student, and it says, I'm a little confused with part 2 of this question. Would it be possible to explain again?
Of course.
That's great. Thanks.
So, part 2. So, we have the graph drawn, and I'm going to probably go on to another page and use that blank to draw it, and I'll erase it then. So, we have drawn, that's g of x, and this is f of x. We accept that they're them. So the question is, where is f of x less than or equal to g of x? And it actually is between here and here. You see the way f of x is less than? In other words, all its values are less than g of x, the function g of x. And they're asking us, what are the values? What's the solution set? In other words, tell us algebraically, for what values of x is f of x always less than or equal to g of x? Well, it's always less than or equal to g of x between x is equal to -7, when x is -7, and when x is 1, in between those values. So between those values, between x is equal to 1 and x is equal to -7, f of x goes below g of x. In other words, it's less than g of x. But if you look at the value, we'll say beyond, we'll say at -9, okay? When it goes up there, and if you look at here, where the function goes up there, and we'll say this is 4. I mean, f of x is greater than g of x beyond -7, because you can see, look, it's way above it. You see, it's in the higher realm of it. Its values are higher. So f of x is greater than g of x between or where x is greater than or equal to -7 and where x is greater than or equal to 1. I hope you can see that. So that beyond those points, the function f of x goes way above g of x. But between those points, -7 and 1, it is less than. In this area here, it is less than. Every point on f of x, every point here is less than g of x between these points. So I hope that answers your question.
I think I've got, so another comment in from a student was, so is it for any question like this, you use the intersection of f of x and g of x and then use the inequality signs?
Correct. Yes.
Thank you.
That's right. Yeah, because the point where they intersect is where the values switch. In other words, where f of x intersects g of x, you know, at one point, from that point on, it's either below g of x or it's either above it. So yes, you must always find the intersection to find the point where the inequality changes. That's it exactly. So find the intersection point. So question 3, the cubic equation 3x cubed minus 7x squared plus 17x minus 5 equals 0 has one integer root and 2 non-real roots. What does that mean? You should straight away know that non-real roots means they're complex roots. So what do you do in this instance? So they want you to find the 3 roots of the equation. Well, normally if you have to find the integer root, which is a whole number. So you've got to test different numbers on this equation to try and figure out what the integer root is first. So you do that first. And then secondly, you find the non-real roots. So the non-real roots have to be found algebraically. So we have x cubed minus 7x squared plus 17x minus 15 is equal to 0. Try 1. 1 minus 7 plus 17 minus 15 equals to 0. No, that doesn't work. So you test like that. Try 3. So 3 3's 9, 3 9's 27 minus 3 3's 9, 7 9 63 plus 51 minus 45 equals 0. As it happens, yes, it does. I've probably worked it out wrong, but 3 is the root there. You can test it yourselves. Okay, so x is equal to 3 is the root, because 3 worked in the equation. So if that's the root, x minus 3 is the factor. So how do you find the rest of it? Well, you divide this known factor into the equation. Okay, x into x cubed goes x squared times. We multiply back, x by x squared by x is x cubed. X squared by minus 3 is minus 3x squared. We draw a line under. We change the sign, that goes. Now we have minus 7x squared plus 3x squared. So that's going to be minus 4x squared. And we carry down our 17x, right? Now, x into minus 4x squared goes minus 4x times. That's minus 4x squared plus 12x. 9 under, change the sign because they're the same, and change the sign here. So they cancel. And we have, sorry, I changed the sign here. So 17x minus 12x gives us 5x. Carry down my constant, minus 15. X into 5x goes plus 5 times, 5x. 5 by minus 3 is minus 15, and we got a 0 remainder. So we now know that x minus 3 multiplied by x squared minus 4x plus 5 is equal to x cubed minus 7x squared plus 17x minus 15 is equal to 0. So that's 1. We need now to divide this into 2 factors or roots. But look at the question before you waste a lot of time in an exam. They've said they're 2 non-real roots, which means that they're complex, which means that the only way to solve this question is using the minus b plus or minus the square root of b squared minus 4ac all over 2a. Now, I'm not sure if I have that written up properly, guys. Minus b. Yeah. So you have to use that formula to solve this last equation here. And the reason being is they're non-real roots. So it's going to give you what you're going to have is in this square root, you're going to have a negative something. It's going to be a negative number. Okay, and that will give you your roots. So you get, because you plus or minus, it's also going to give you 2 roots. And they're your answer to the question. So the first root is, so we know that x is equal to 3 is 1 root. The second root that you solve is going to be x is equal to 2 plus I. And the third one is x is equal to what? 2 minus I. Because remember, if you have 2 roots, 2 complex roots in an equation, one is the conjugate of the other. So if you know one, you'll always be able to find the other by changing the sign of the imaginary part. So there are your 3 roots. That's it. Simple and straightforward. That's a very common question to come up. So the next one is solve for x, where x is an element of the natural numbers, and we have square root signs.
Sorry, Suzanne.
Yeah.
There was a question came in. I don't think it was connected, but maybe it was. It said, can you go over the minus b part again, please?
I can, absolutely. So, okay. So just to go back a little bit, when we divided in x minus 3 in, we ended up with this formula here, this equation here, and we need to find the roots of this equation. So in order to find the roots of this equation, you could try and factorize it like this, with your x and your x, but the problem is you're not going to find whole numbers here, and the reason I know that is because they've told us they're non-real roots. So you have to use what's called your minus b formula, and what happens in that is so for this equation, x squared, a is equal to 1, b is equal to minus 4, because a and b and c are the coefficients of x. So a is equal to 1, b is equal to minus 4, and c is equal to 5. So you substitute them into your formula. So you have minus b, which is minus 4. Please someone correct me if I have the formula incorrect. So it's minus 4 plus or minus the square root of b squared, which is minus 4 squared, minus 4 times 1 by c, which is 5. And it's all over twice a, which is 2. So this is going to give us plus 4 plus or minus the square root of minus 4 squared is 16 minus 20. So it's going to give me the square root of minus 4. As I said to you previously, if you get a minus in there, you know you have a complex number, and it's all over 2. So if we divide 2 into that goes twice. I can't divide it into that one. What you do here is you break up the square root of minus 4, can also be written as the square root of minus 1 by the square root of 4. Do you remember that with your square root rules? So we know that the square root of 4 is 2 by the square root of minus 1. So that means this can be written as 2. Right, so I was on the minus b formula, and I had 4 plus or minus the square root of minus 4 all over 2. And I said you can rewrite it as 4 plus or minus the square root of 4 by the square root of minus 1 all over 2. And that's equal to 4 plus or minus 2 times the square root of minus 1 all over 2. Now we can cancel. That's 2, that's 1. That means we're left with x is equal to 2 plus or minus the square root of minus 1, which is I. We know that the square root of minus 1 is I, so it's equal to 2 plus or minus I. So that means x is equal to 2 plus I, and x is equal to 2 minus I. They're the two complex roots. I hope that explains it for you. Those are the two complex roots using the minus b formula. So the minus b formula is used to solve a quadratic equation when you don't have whole numbers. If you can solve it yourself, it's the quickest way to go into it. But usually, if you end up with a negative in the square root, that means you're going to have a complex number, or as the question says, non-real roots. So that's your indication. If it's non-real, it's going to be complex, which means you'll have to use the minus b formula to solve. Okay, right, move on. So I suppose, well, look, we'll just finish part B of this. Yeah, we'll finish B, and then we'll take a break for 10 minutes.
Okay.
So quickly, part B. So you have to solve this equation. What's the problem with this equation? It's the square roots. If you square both sides, this will work out nicely if you squared both sides, because the squared would cancel the square root. But on this case, it won't. You got to be very careful. Here's where they're trying to trick you, because there's two different elements in this. There's a square root of 3x minus 5, and there's also a minus 3. So if you're to square that, you have to square this part like this. So there are two different elements. What you do is you square both sides, so you have the root of 3x minus 5 minus 3 by the root of 3x minus 5 minus 3. And that's equal to x minus 6, because the squared there has cancelled the square root, but not in this case, because you've got two parts, like an a and a b. Okay, so now we know that the answer to that, if you have an a and a b squared, an a minus b squared, the answer is a squared minus 2ab minus 2ab plus b squared. That's your formula when you have an a minus b squared. And here we have an a minus b. And in this case, our a is square root of 3x minus 5, and our b is 3. So our answer to that is going to be the square root of 3x minus 5 squared minus twice a by b. So it's going to be 3 times 3x minus 5 plus b squared, which is minus 3, which is 3 squared. So that's equal to, here now we have a square root and a squared, so one will cancel the other. So we end up with 3x minus 5 minus 6 times square root of 3x minus 5 plus 9 is equal to x minus 6. And we work our way down through that, and we are left with 3 across. No, we haven't. 3 minus 5. We bring the x minus 6 across, and that gives us 3x minus x minus 5 plus 6 plus 9 minus 6 times 3x minus 5 is equal to 0. So 3x minus x is 2x. Minus 5 plus 6 is 1 plus 10. Minus 6 into root of 3x minus 5 is equal to 0. So cancel the 2's, and we'll end up with x plus 5 minus 3 times the square root of 3x minus 5 is equal to 0. And we take it up here, and it means we have 3 times the square root of 3x minus 5. We bring the x plus 5 across again, and I'll show you why, is equal to x plus 5, right? So again, we're left with another square root that we have to get rid of. So we square both sides, but this time it's much easier because these are multiplied by each other, and the square root, the 3x minus 5 are under the square root. So you square both sides again, get rid of this square root. If you square that, is equal to x plus 5 squared. So now we end up with 9, don't forget to square the 3, by 3x minus 5 is equal to x squared plus 10x plus 25. So that gives us 3 times 27x minus 45 is equal to x squared plus 10x plus 25. And that gives us x squared minus 17x plus 70 equals 0. And x is equal to 10, or x is equal to 7. So the trick in this question was square root. The fact that on this side you had 2 elements, so you had to square it like an a minus b squared. When you worked your way down, you got to another equation. Here you still had another issue with another square root in the equation. So by moving x plus 5 across and out of the way, it was easier to square across. And your square root then is cancelled by the squared, and you end up with another equation that you can solve. And luckily, they make it very easy to solve at the end, because that's not the crucial trick in it. The crucial trick is getting caught with these square roots and knowing how to square them. So we'll take a break.
Okay, see you back here at 11:18.
So welcome back, everyone. And yeah, we'll move on to question 4, which, as we said, is complex numbers. So our first part here is simplify I to the power of 57. So that may look like a really complicated question, and sometimes they're much simpler than you would have thought. For instance, what do you know already about I? I is equal to square root of minus 1, and I squared is equal to minus 1. So we can break this up into a number of I squares. So we could also write it as I to the power of 57. is equal to I to the power of 56 by I, which is equal to minus 1 to the power of 28, because there's 28 I squareds in I to the power of 56 by I. What's the answer to that? Well, minus 1, any negative number to an even power is always going to give you an even answer. But that is 1 by I, which is equal to I. So your answer is equal to I. Simple as that. All right. So that's question 4A. We move on to question 4B. So the complex number z is equal to 5 plus 3i, where I squared is equal to minus 1. Find the complex number w is equal to a plus bi, such that z by w is equal to 2 minus 26i. So in other words, find the imaginary w, or find the other complex number w. So what we would do then is, we know that they're telling us that ZW, so that's 5 plus 3i by a plus bi is equal to 2 minus 26i. So we multiply it out and see what we get. We get 5a plus 5bi plus 3ai minus 3b is equal to 2 minus 26i. Now, we have real numbers and imaginary numbers, so we need to put them together. So for instance, let's start with the imaginary numbers here. And we know that in any equation, the imaginary numbers are equal to the imaginary numbers and the real numbers are equal to the real numbers. So that being the case, we know that 5bi plus 3ai is equal to 26i. We know that for a fact. And we also know that 5a, which is real, 5a minus 3b is equal to 0, because there's no real number over on this side. It's 0. 0. So we solve. So we take out the i's here, because we have I across the board. So we have 5b plus 3a is equal to 26. That's one equation in two variables. And we also know this one, which is another equation in two variables. So you're going back to very basic simultaneous equations to solve them. So when you work these out simultaneously, you get a is equal to minus 2, and we get b is equal to minus 4. Therefore, w, which is equal to a plus bi, is going to be minus 2 minus 4i. So that's straightforward. So the key to remember in this question is that the real part is equal to the real part of another equation, and the imaginary parts are equal to the imaginary parts. That's the trick. Any questions?
Sorry, Suzanne. Yes, there's a question just right. I was trying to figure it out there. I couldn't. But it says, where did the 2 go? And I suppose it's the 2 at the start.
2 at the start. Ah, it did get lost, didn't it? I dropped it by accident. That's what happened to it.
Okay.
So let me correct that. That would be 2 minus 26i which means we would have 5a minus 3b is equal to 2. And that will, they'll solve correctly because I have them already solved. Those are the correct answers, but I did make an error there. Thank you for that correction. Yeah, I forgot about that because we had, if anybody's looking and wondering where did that question come from, someone said, where did I lose the 2, which is this 2 here. So all of this equation should have been equal to 2 minus 26i, which I dropped in error. Thank you for that. So now we have the complex number w is equal to minus 2 times root 3i. Write it in polar form. Very common question that you get asked all the time. So what do you need to know for polar form? For polar form, you need what? You need the modulus, and you need the argument. The word for the argument, the angle. The angle the modulus makes with the x-axis. Okay. So we have, for a typical complex number, we have z, I'm going to call it z, or w, is equal to r times cos of theta plus I sine theta. That's your typical polar form. So your modulus is the r, and your argument is theta. So how do we find those? Well, r we know is the square root of a squared plus b squared, which is square root of, what's b, minus 2 squared, or it's a plus b. So a is here, and here is b. Minus 2 squared plus minus 2 root 3 squared. Remember, you don't bring the I with you. It's only the whole, it's only the actual number, the coefficient of it. And when we calculate that, we get minus 2 squared is 4, and minus 2 root 3 squared is plus 4 times 3, because remember the squared and the square root cancel each other. So that's equal to the square root of 16, which is equal to 4. So our modulus is 4. What's our angle? What's the angle that it makes with the x-axis? Well, what's the formula for an argument? It is tan of theta is equal to a over b. B over a. B over a. So the inverse tan of b over a is equal to the argument. And in this case, we have the inverse tan of minus 2, minus 2 root 3 all over minus 2. Minus 2 is cancelled, so we've got root 3. And the answer to that is, what I got down here, minus 2 root 3 is, sorry, now I'm getting mixed up. Is 240 degrees. Now, how do we work that out? What's most important about the angles? So if we were to draw this angle, which I often do to visualize it on the Argand diagram. So we know that A is, remember this is I, and this is R. What's the real part? The real part is minus 2. So we're down here at minus 2. and the B part is minus 2 root 3. So we have 3, 2, what's down here about 2.3. So down here minus 2 root 3. Okay. So if you were to draw that point, this is W. This is the complex number of minus 2 root 3 I. And this is the angle theta, and this is R, the modulus. We want to know what angle it makes. So the angle that it makes, root 3, is 60 degrees. So when we work out here, we get 60 degrees. Okay? But we don't know where on the, is it 60 degrees here? Is it 60 degrees here? You have to check and see which quadrant it's in. Because they're both negative, it's down here in this quadrant. So the angle we make here is 60 degrees. But how many more angles have gone before it? 180 degrees have gone before it. So 180 degrees plus 60, which means that our theta is 240 degrees. So our answer is W is equal to 4 times cos 240 degrees plus I sine 240. Anyone have any questions on that? This is a very common question that you'll be asked to convert between polar form and rectangular form.
Sorry, Suzanne, there was a question came in, but you answered it just at the same time. It was about putting the numbers into the calculator and get 240, but it depends on which quadrant you're in. So you've answered it. It's
very important which quadrant you're in, and that's going to be probably one of the most challenging things about complex numbers. Is I always do it. You have to draw the Argand diagram very quickly and see which quadrant you're in and see which angle it is. Because you can't depend on what comes up in your calculator, because it doesn't know how many quadrants have gone before. So it will probably spit out 60 degrees and not 240. Right, so that's simple as. The next part is question 2. Using De Moivre's theorem, solve the equation z to the power of 4 is equal to minus 2 root 3i. So De Moivre's theorem is straight away associated with polar form, and I look on De Moivre's theorem as a cool tool. It's a way to evaluate something which has a really high power, like if you were given a complex number to the power of 56. De Moivre's theorem helps you calculate that very quickly without having to laboriously multiply one by the other, by the other, by the other. So instead of dreading De Moivre's theorem, you need to look at it as a really, really nifty tool. However, with De Moivre's theorem to work, you have to be in polar form. And what's happened here in this question is part 1, they've already got you to convert into polar form. So you're already part of the way ahead. So I'm just going to erase the Argand diagram here to give a space. And we'll continue on down with that. So they want us to evaluate z to the power of 4, which is minus 2 root 3i to the power of 4. So how do we do that? Well, we already know that with de Moivre's theorem, we write this in the general form. So what they're saying is, this would happen to me in the exam, I'd go off on a tangent, but it's completely differently. So what they're saying is, solve it when z to the power of 4 is equal to -2 root 3i. They're not saying put this to the power of 4. They're saying z to the power of 4 is already equal to that. So how do we solve for z then? So to find z, it's z to the power of 4, the power of a quarter, is equal to -2 root 3i to the power of a quarter, in order for us to get from z4 back to z. I hope you understand that. That means z is equal to that. So that means z is going to be equal to 4 to the power of a quarter by cos of 240 plus I sine 240 to the power of a quarter. And remember, with de Moivre's theorem, when you have z, you can multiply in the power of the polar form into the angles. So what you're left with is 4 to the power of a quarter is square root of 2 by cos of a quarter by 240 plus I sine a quarter by 240. That's the beauty of de Moivre's theorem. It lets you multiply in the power rather than trying to multiply up or try and find the fourth root of it. But that gives us very nicely z is equal to 2 times the cos of quarter of 240 is 60. That's 60 plus I sine 60. But the thing to remember here is that z to the power of 4 and z to the power of a quarter, what we're actually finding is we have 4 roots. We have 4 solutions to this. Okay? So the solutions come in terms of n. N is the general form for finding. We use the general form when we're estimating the polar form and applying de Moivre's theorem. So the general form would be z is equal to z to the power of 4, which is the original one we were given, be equal to 4 times cos of 240 plus 360n plus I sine 240 plus 360n. Why do we have the 360n? Because you have 4 solutions to this problem, because it's z to the power of 4. So if you had a quadratic, it would be 2 solutions. If you had a cube, you'd have 3 solutions. When you have z to the power of 4, you have 4 solutions. And because the complex numbers would have been a number of times around the Aragon diagram, we have to include 360 degrees by n to calculate for every time it's been around. Okay, so that's your general form that you have to use. So in that case, we have, after quantifying it, z is equal to root 2 times the cos of 60 plus, we've divided it by 4, plus 90 n plus I sine 60 plus 90 n. Okay, so when n is equal to 0, z is equal to 2 times, I'm going to say cos of 60 plus I sine 60. When n is equal to 1, z is equal to root 2 times cos of 150 plus I sine 150, and so on and so forth. N is equal to 2 and n is equal to 3. And then you evaluate each of those. So we'll evaluate those on the next page. So any questions, please ask.
Sorry to interrupt, Suzanne. I do have one question in here. I just was trying to figure it out, but maybe you can. It says, so is 4 cos 240 plus 360n plus I sine 240 plus 360n equals minus 2 root 3i.
It is, but that's the question at the start. Yeah, it is. But we've expressed it. We've expressed the minus 2 root 3i in its polar form and in its general polar form, which brings in the plus 360n. So that accounts for the number of rotations that we'd have around the Argand diagram. So I'll go on to a page here, and what I'm going to say to answer the person's question, they asked, I had a z power of 4 is equal to root 2 times the cos of 240 plus 360n plus I sine 240 plus 360n. And that is, as you quite rightly said, minus 2 minus 2 root 3i. Okay? So if that was just z, we didn't have the 4 there. We wouldn't need the 360n because n would be equal to 0. And we would only be dealing with cos of 240, which would be the Argand diagram here. And this is the spot. So this angle here would be 240. And we'd only be dealing with z here is equal to one value, right? The problem is that we're trying to solve this equation, which is z to the power of 4, which has 4 solutions or 4 roots, okay? Which would be like if you were solving an x squared plus 3x, you'd have x is equal to 1 something and x is equal to 2. You'd have 2 roots, okay? So in this case, because we're trying to solve for z, we want to solve for z is equal to what? Well, we do know there has to be 4 solutions. And while the angle it makes with the x-axis has to remain at 60, well, it could spin around. It could spin around 360 times for the second root. It could spin around another 360 for the third root, and so on and so forth, which is why we have to give different value. We have to evaluate for every solution where n is equal to 0, n is equal to 1, n is equal to 2, and n is equal to 4. If that was only z to the power of 3, we'd only have 3 solutions. N is equal to 3, n is equal to 2, or no, it would be n is equal to 0, 1, and 2, and this is 3. Okay, so that's why. So your general format. Oops. If you look at in your textbook, this is the general, called the general polar form. And you have to use that when you're solving for z to the power of something. So we know we have to get z, which means we had to put this to the power of a quarter in order to get to z, which means all of this has to go to the power of a quarter. So now we have z is equal to root 2 to the power, did we have the root 2 in there? To the power of a quarter by cos of 240 multiplied by a quarter, or sorry, write it down first, plus 360n plus I sine 240 plus 360, all to the power of a quarter. Okay, so that's what we have to solve. but, sorry, 360n. But we know with De Moivre's theorem, we can multiply that in there, into the angle, multiply that in. So we get z is equal to root 2, I think that should be 4, is it? To the power of a quarter times cos of a quarter of 240 plus 360n plus I times the sine of a quarter of 240 plus 360n. That's De Moivre's theorem. That's by De Moivre's theorem. Okay, it helps us to do that, which means we get. Someone check for that me there. Is that fourth part? I think that's root 2 there. So that gives us then by the cos of a quarter of that is 60 plus 90n plus I times the sine of 60 plus 90n. And then you evaluate forever n is equal to 0, n is equal to 1, and n is equal to 2, and n is equal to 3. So for n is equal to 0, it just ends up being root 2 times the cos of 60 plus I sine 60. And you can evaluate that in terms of it's root 2 by, what's the cos of 60? I think it's a half, plus root 2 by 3 over 2. Root 3 over 2 is the sine of 60 by I. Yeah? So that is equal to root 2 over 2 plus root 6 over 2i. Then the next one is when n is equal to 1, it's root 2 into cos of 60 plus 90. So it's 150 plus I sine 150. And that's going to be root 2 times minus, it would be root 2 times into minus root 3 over 2 plus a half, because sine of 150 is a half, I, which ends up being minus root 6 over 2 plus root 2 over 2i. The next solution is n is equal to 2. So it's going to be root 2 times cos of the 180 and 60 is 240 plus I sine 240, which ends up being minus root 2 over 2 minus root 6 over 2i. And then n is equal to 3 ends up being root 2 times the cos of, what we got, 240 and 90 is 330. 330 plus I sine 330. Am I right? Is equal to, and that ends up being root 6 over 2 minus root 2 over 2i. Okay, so they're all the solutions. In other words, z is equal to that, and z is equal to that, and z is equal to that, and z is equal to that. Same as when you evaluate or you solve a quadratic or a cubic equation, you get x is equal to this, x is equal to that, and x is equal to that. If you turn all them into factors, multiply them all up together, you will come back to that. You multiply them all. But they're all roots. You can turn them into factors. Take time to study this slide when you go back and rewind it, but hopefully you get a bit more of an understanding of it. Okay, so that was that. That was De Moivre's theorem. So that question basically takes in everything you need to know about complex numbers. If you can do questions like that, you have it nailed. But you have to spend time on it. The general form for De Moivre's theorem is very important. So let's jump to 9. So this is about acceleration and rates of change. Again, very, very topical and important to get right in your head. We have a spherical balloon being inflated at a rate of 3 centimeter cubed per second. They want you to find the rate of change of the radius of the balloon, and they're telling you that it's dr dt you're looking for when r is 3. And they also want you to find the rate of change of the surface area of the balloon, and they're telling you that's dA dt when r is equal to 3. Now, very often they only give you the description, they don't give you the numerical dr dt or dA dt, so this is very helpful. So what we start with first is a spherical balloon is being inflated at a rate of 3 meters cubed per second. So what is that? D what, D what? So the rate is, a spherical balloon is being, so what is centimeter cubed? Centimeter cubed is volume. So volume. So the rate of change there is what's changing. It's the volume is changing. So dV dt is equal to 3 centimeter cubed. That's what's important to establish. Its spherical balloon is being inflated at a rate of 3 centimeter cubed per second. So every second it's increasing in volume. So that's dV dt. Now they want you to find the rate of change of the radius of the balloon, dr dt, when r is equal to 3. So we're looking for in this dr dt. Dr dt. And we know that that's made up of dr dv by dv dt. Why? Because if you look at it like this, that can cancel with that and you're left with dr dt. So you need to find the derivative, a derivative that has r and v in it, and you already have dv dt. You've been given that, remember? That's 3. So now, first of all, you need to find dr dv. So the volume formula is what? The volume of the sphere is equal to 4 over 3 pi r cubed. Sorry, 4 over 3 pi r cubed. That's your formula. So V is equal to that. So what's dV dr? In other words, what's the derivative of V with respect to r? Remember, there's r here in the equation because it's V is equal to 4 over 3 pi r cubed. So we differentiate volume. The dV dr is going to be 3 by 4 over 3 pi r to the power of 2. Remember, we increase the power. That cancels with that, so we're left with 4 pi r squared. So now we know that dr dt is equal to 4 pi r squared by 3, which is equal to 12 pi r squared. And the question is, when r is equal to 3, what's that? So let me check. But this one here is dV dr. What we're looking for up here is dr dV. You've got to invert it. So twist it around, get dr dV is equal to 1 over 4 pi r squared. You can flip it upside down to get dr dV. So that means that dr dt is equal to 1 over 4 pi r squared by 3, which is equal to 3 over 4 pi r squared. If we substitute in the value for 3, or the value for r at 3, we get 0.03 centimeters per second. Okay, so that's the first part. The second part is, what is the rate of change of the surface area, which is dA dt when r is 3. So what's the surface area dA? So where do we have a formula with regard to A? What's the surface area of a sphere? So now they're looking for dA dt. So what's the surface area of a sphere? It is, let me have a look. Surface area is 4 pi r squared. It is 4 pi equal to 4 pi r squared. The a d r, remember it's r is the variable there, so the a d r is going to be 8 pi r. And what are they looking for? They're looking for dA dt. So dA dt, what can that be made up of? Well, we already have dA dr, so it has to include that. So it's equal to dA dr multiplied by something top and bottom that'll give us dA dt. So we want something dt down here, and we want dr up here, dr dt, I'd say. That would cancel with that. That would give you dA dt. Yeah, so that's right. dA dr by dr dt. So what's dr dt? We've already got it, haven't we? In the previous question, dr dt was 3 all over 4 pi r squared. So our answer is going to be dA dr, which is 8 pi r, multiplied by 3 all over 4 pi r squared. R's will cancel r here, pi's will cancel there, 4 there, 2 there, which is equal to 6 over 4, I make it, 6 over r. And when r is equal to 3, is equal to 6 over 3 is equal to 2 centimeter squared per second. Okay. So what's important here is that this is where people get confused. How to make up, when you know this is what you want, how to make up what combination of derivatives would give you. Remember, these derivatives can be flipped upside down, dt over dr, to make them fit so that you have the right combination. So just because you're looking for dt dr, you can find dr dt and then flip your value. So that's it. That's everything. That's question 9 finished. We've done as far as question 5. So 6 and 7 and 8 weren't done. So I hope that went okay for everyone. I must apologize for the technical difficulties I was having. I was working in presenter view, the annotation of PowerPoint, and it was very annoying the way it was popping up menus, so it distracted me a bit, and my apologies for that. But I hope you enjoyed it, and best of luck in your exams. Take your time when you're doing all this work, and I hope you go back on all these questions again as the year progresses and you get value out of it.
Thank you very much, Suzanne. You've done quite a few questions there today, Suzanne, and it was a great presentation overall. I think, thank you very much for doing that. It should be a great help for the students, especially now the Christmas exams are coming up. But also in the future, hopefully if you practice these type of questions, you'll get a good mark. Once again, thanks, Suzanne, and bye for now.